axis of rotation, and radians. Up until now, this course is focused on translational, that is, linear and uniform circular motion. All objects have been treated as a point mass. Uniform circular motion explained how a point mass rotates about a point external to its shape. It is now time to address the rotational motion of objects and how their physical structure impacts this motion. Rotational motion is when an object rotates about itself and has an extended physical mass. For example, a disk, sphere, or a block, not just a point. What are some types of rotating objects and how are they important to society? The list is endless. Here's some examples. Turbine generators that change mechanical energy into electrical energy and supply electricity to businesses and homes. Helicopter blades that lift the helicopter into the air. Electric motors that power cars, circular saws, and vacuum cleaners. Swivel chairs. Curveballs thrown by baseball pitchers. Automobile and truck tires that propel them down the road. Rotational kinematics is the study of the rotational motion of extended objects without considering the forces that put them in motion, and will be studied first. The next unit will cover rotational dynamics that explains how the forces on extended masses impact their rotational motion. Extended mass objects rotate about a line somewhere within the object called the axis of rotation. Assume that all these objects are rigid bodies, that is, they keep their shape and are not deformed in any way by their motion. Here's a sphere rotating about its axis of rotation, the vertical red line. Does the axis of rotation have to be part of the rigid body? No. If you were to spin this donut around its center, the axis of rotation would be in the donut hole, pointing out of the page, right here. That's where the axis of rotation is. Degrees. There are several theories why a circle has 360 degrees. Here's a few. If you're interested, there's a lot of information on the web. Some people believe it stems from the ancient Babylonians, who had a number system based on 60 instead of the current base 10 system. Others track it back to the Persian or Biblical Hebrew calendars of 12 months of 30 days each. But it has nothing to do with the actual geometry of the circle. There is a more natural unit, the radian. Assume this circle is rotating about its middle, right over here. The axis of rotation is pointing out of the board. Start with the piece of the circle at point A. As the circle rotates counterclockwise, the piece of that circle reaches point B. The point traveled a distance of S, called the arc length, along the circumference, and swept out an angle theta, right here. Move from A to B, and it consumed that much of the angle. We call that the angle theta subtends an arc length of S. The points A and B are always at the same distance r from the axis of rotation. That's what it means to be a circle. Define this angle of rotation theta as the ratio of the arc length S to the radius r of the circle. And here's what it's going to be. Theta is going to be equal S over r. Can you see how this is a much more natural definition of the angle of rotation than basing it on an old calendar or arbitrary numbering system? Instead of using the arbitrary degrees to measure angles, the angles are now defined in geometric terms as the ratio of an arc length and the radius of the circle. The unit for theta is the radian. Radians are actually unitless since they are the ratio of two distances, right, S over r, but they are used to show the size of the angle theta. When a point on a circle rotates and comes back to the same point, it has performed one revolution. It starts at point A and rotates until it returns back to point A. What distance S was covered? How many degrees were swept by this full rotation? The point moved around the entire circumference, so it traveled a distance of 2 pi r, circumference of a circle, while an angle of 360 degrees was swept through. We are now going to use the radian definition to find the conversion between radians and degrees. So we have theta is 360 degrees. That equals S over R. S is 2 pi r, the circumference that we covered. R is the radius. And we get 2 pi radians. So 360 degrees equals 2 pi radians. Divide both sides by 2 pi, and we find that 1 radian is equal to 57.3 degrees. When an object makes one complete revolution, it sweeps out an angle of 360 degrees, or 2 pi radians. 1 radian is equal to 57.3 degrees. The radian is frequently abbreviated as rad. Be careful about the settings on your calculator. Up until now, you probably just had angles set for degrees. If theta is expressed in radians, the calculator needs to be set for radians. Example 1. How many radians are subtended by a 0.20 meter arc of a circle of radius 0.80 meters? Here's our given, the arc length and the radius of our circle. We use theta is S over R, substitute in our variables, and we find that the radians equal 0.25 radians. Example 2. How many degrees are in pi over 3 radians? One complete revolution is equal to 360 degrees, or 2 pi radians. So we set them equal to each other. Divide each side of the equation by 2 pi to find the number of degrees in 1 radian. So we have 1 radian is 180 degrees divided by pi. And we're going to use that coefficient to find the number of degrees. So we have pi over 3 equals pi over 3 times 180 degrees over pi. We have the pi's cancel out, and we get an answer of 60 degrees. An eraser is placed at the edge of a rotating disc with a radius of 0.30 meters. What is the travel distance by the eraser if the disc describes an angle or subtends an angle of pi over 6 radians? The radius is 0.80 meters. Theta is pi over 6 radians. We use our equation. We solve it for S by multiplying both sides by R, substitute in the givens, and we get S, the arc length, is 0.16 meters.